done in the mean vertical net flux in a shrink box, something I've done mostly with Geoffroy Le Sur. There have been some recent things in progress with quite a number of other people, but I won't have time to speak about that. So. And anyway, it's still in a messy state, so it's all right that I don't have time to speak about that. Okay, so the problem is the simplest you can think of in some respects. So it's a shearing box with a mean vertical field, rotation, constant shear, the equations of the deviation of velocity and magnetic field from the mean are right here. It's incompressible. You don't even have to worry about an equation of state. So it's a spectral code, actually, that we're using to do that. And it's also simpler in the sense that the linear physics is, at least in some sense, better understood there. OK. Again, yeah, to go back to the point of Jim right now, the only dissipation, there is explicit dissipation. If you don't put explicit dissipation in a spectral code, it just explodes. So you don't, because the numerical dissipation is basically 0. So you need to do that. And we do only resistive dissipation. I'm afraid that we would all like to know what's going on with ambipolar and Hall diffusion, but we're not quite there yet. It's already a real mess like that. OK, so the linear physics first, because it has some importance for this problem. Since the beginning of the MRI studies, it has been known that with a net vertical flux, some special solution known as the channel flow plays a special role. It's a flow which happens linearly and is also a nonlinear solution, which is counter-propagating in the vertical direction flows. And it produces radial magnetic field from the vertical one. And also because of the shear, it also produces azimuthal magnetic field. And then you get transport from the correlation of the two, just in the linear problem. The growth rate of the instability, the maximum growth rate in ideal MHD without dissipation is constant and is set by the shear. It's whatever the wavelength of the instability of these modes. They can have various vertical wavelengths. The maximum growth rate is always the shear divided by 2. When you add some dissipation, and the situation I'm most interested in is when the viscosity is small compared to the resistivity, so that we're in a small Prandtl number regime, which is the one relevant to protoplanetary disks, you decrease this growth rate by a factor which is inversely proportional to the resistivity. This is what's shown here. In the ideal regime, maximum growth rate, and there is a decrease due to resistivity. Eventually, if resistivity is too large, the instability shuts down. Okay, these channel modes are prone to secondary instabilities known as parasitic instabilities. They show up in the form of either Kelvin-Helmholtz type or Turing mode types instabilities. They have a growth rate which is proportional to the channel mode amplitude itself, so that eventually the channel mode, whatever you do, will be broken by these secondary instabilities. And the most unstable such instabilities have a horizontal wavelength in the horizontal direction. What is the... there was some kind of a stick. Oh, it's on the table, sorry. Their wavelength in the horizontal direction is typically twice as large as the vertical wavelength of the channel mode. Okay, so for a long while, and I guess we can say that this has been noticed that in narrow boxes, that is one-to-one aspect ratio and elongated in the phi direction, this is vertical, this is radius, and this is phi. Especially if you're not too far from the critical stabilization by magnetic tension, there are bursts of transport. This is transport versus time. This is the Reynolds stress, the Maxwell stress, and the Thornton stress, which is basically dominated by the Maxwell stress. It bursts, and the bursts are related to the appearance of the channel mode. So it has been kind of surmised for a while that possibly you have some kind of a scheme like that in which the linear instability would be the source, the transport would be dominated by the channel mode, it would be broken up by the secondary instability that I just spoke about, which would act as a sink and produce a parasitic mode, and then through some unspecified nonlinear transfer you get smaller amplitude and kind of random motions out of which you replenish the channel mode. And this part of the statistical equilibrium, that is sink equals source, has been recently quantified by Pess and Goodman. Okay, and so keep that in mind. One of the recent things which has come up in the MRI is this question of Prandtl number dependence. So it appears whatever the field geometry. In this case, it is what we've initially found with Geoffroy in 2007. And this is the transport. This is the Prandtl number. You have some kind of a correlation. The Prandtl number is just the ratio of viscosity of a resistivity. And there is some kind of a power law dependence with a 1/3 index. There is also it has been known for quite a while that the transport also depends on the field strength. So the main issues I'm going to address in this talk, now that I've gone through the introduction of it, is what is actually the role of the linear and quasi-linear physics there. That is the linear, the channel mode, the quasi-linear, the parasitic modes, and also can we say anything about what's going on at low viscosity, that is very high Reynolds number, a small Prandtl number, which is the situation which is relevant for post-planetary disks. So I'm going to attack that through simulations. This is just to exemplify the aspect ratio we've been using, the resolution we've been using. These are spectral code resolutions, so if you want to compare with a finite difference code, you have to multiply that by a factor of 2, basically. So these are pretty resolved. And also, there are 3 runs with a resolution which is twice as large as that. There are quite a number of dimensionless numbers of interest in the problem. Okay, alpha is just the dimensionless Reynolds and magnetic stress. There is the parameter describing the field strength. There are 2 parameters describing the dimensionless viscosity and resistivity, the usual Reynolds and magnetic Reynolds number. And it's, as you know by now, it's extremely important to take that one into account. So basically, your transport depends on 3 parameters, the field strength and 2 dissipation parameters, which I've chosen to be the Reynolds and the Prandtl number. Okay, this summarizes all the new results, and I'm going to discuss that for a while. So there are quite a number of information there. This is, again, transport versus Prandtl number. The code color is the field strength. This is a field strength is decreasing this way. The symbol code is Reynolds number. And I'm going to discuss this a little bit more later on. Some special runs are shown with different color code. This one is the highest resolution we have done, and it's also the lowest Prandtl number we have reached. And it's the lowest ever reached, I guess. It's 1/16. It's still pretty large compared to whatever you have in the real disk. And these are the three high-resolution runs I mentioned earlier. They are done not at beta equals 100, but beta equals 1,000. There is a noticeable increase of transport with increasing Reynolds number. These 3 runs here, and I put them here just for Jim's sake, because they are from his the ones he showed in Grenoble. It's the runs that he has made in with the same configuration, and kind of fits into the general thing. Okay, so first thing, we have changed the aspect ratio. We have increased considerably the resolution, and to some extent increased the Reynolds number. This hasn't changed the slope of the Prandtl number dependence at the highest field strength we have looked at. This has changed the amplitude of that. This thing is changing the aspect ratio has moved this thing down, but has not changed its slope. And that's because by enlarging the box size, you kind of make the channel more less important, basically. As I just mentioned, there is a system. We didn't see that in 2007. There was too much noise. But we spent something like 100 times more numerical hours there. So it's now possible to see that there is indeed a systematic increase of the transport with Reynolds and a constant Prandtl, then with Reynolds and magnetic Reynolds number. Okay, there is a lot of information there, so I'm going to break it up in various pieces soon. But first, what's there? It's the same thing here. What's shown here is a composite plot of the growth rates. So here is Reynolds number. Here is field strength, decreasing field strength. This is the wavelength of the channel mode. This is their growth rate. And there are 3 different curves per plot. They correspond to 3 different Prandtl number, 1, 4, 1, 4, 1, 4, 1, 4, the ones which have been looked at. So that kind of covers all the growth rates that are going on here. And the crosses are the modes which are actually present in the box. Okay, so let's break that up a little bit, otherwise it's really incomprehensible. If you look at these 2 subsets of results, that is most, not all, but most of the ones at the largest field and some at the intermediate field strength. These results have, these guys have, well, the linear modes, the linear channel modes have a growth rate which is basically constant. It's basically, for these guys, the growth rate of the inviscid and non-viscous and non-resistive. It's ideal MEG growth rate. They achieve ideal MEG growth rate. So the first conclusion is that at least this Prandtl number dependence, the one, the one here, the Prandtl number trend here does not depend on the growth rate. That's been a question which has been asked a number of times. At least for these ones. I'm not saying for the others, at least for these ones. Now if I look at another subset, these and these, which correspond to these things here, we find that the field strength dependent is not related to the growth rate either. It's a question which we should have asked, I guess, earlier. Okay, that's what I'm saying here. Now for the rest. For the rest, there are basically 2 regimes. What's there? It's transport. It's all the points I've shown on the previous graph. It's transport versus growth rate. The runs I've just looked into, the special ones which don't depend on the growth rates, are here. Basically, the transport is really independent of the growth rate. And beware that this is a log linear scale. The previous one was log-log. So it's really independent of the growth rate in this regime here. And there is a clear exponential dependence of the growth rate for all the other modes. The dispersion here is real. It's not numerical noise. The error bar on these things is much smaller than the dispersion, and it does contain information at every constant growth rate. It's probably some information about Prandtl number dependence, but there are so few points per growth rate that I still not sure what it means. But there is some real information there. Okay, so for the first question, does the Prandtl number dependence depend on the linear physics, that is the one we understand well, which is the growth rate? The existence of a Prandtl number dependence is not related to that. The details of it are when we don't reach large enough as that's the numbers you asked. But basically, the existence of that is not related to that. Now, the next question is that related to the existence, is the transport saturation, the transport level that we observed related to the existence of parasitic modes and the fact that parasitic modes might break up the channel mode. And this has been quantified, as I mentioned earlier, by Pessa and Goodman. They used a very simple criterion that's saying that the growth rate of the parasitic mode being equal to the growth rate of the channel mode is exactly where the channel mode produces the transport. So they look into this criterion, quantify the transport, look if it depends on Prandtl number. This is the resulting transport versus Prandtl number. They looked at that for this large large field strength, and for the very largest Reynolds number that we have used, they find that there is basically no dependence. It's a linear scale. No, linear log, sorry. Whereas we do find some dependence, and I remind you this is a log-log scale. The dependence is really sharp compared to this very flat thing. And it's kind of normal. There is no reason that these large Reynolds number and magnetic Reynolds numbers, the channel mode is a large scale mode. The parasitic modes are large scale modes. Again, there is no reason that they are really affected by dissipation. So the conclusion for this question is most probably just channel mode and parasitic modes alone can't explain the transport saturation, the magnetic Prandtl number dependence on transport. Okay, now I'm going to look in some more detail at what's happening for the very large. With respect to what we can do, with respect to what nature does, it's pretty ridiculous, but anyway. Large Reynolds number and an intermediate field strength. I've written here the energy budgets, the velocity and magnetic field energy budget. There is, where am I? Oh, it's all right. There is an injection term, which is actually the transport term. The energy injection term is the transport term for velocity and magnetic field. There is a dissipation term related to viscosity and resistivity. And in between, there is some exchange between the two that disappears when you sum them up. This term in a box average sense is opposite to that one. They differ by a divergence. So in a box average sense, they differ, but they describe the exchange between the two. And this is the physical interpretation of that one is that it's the rate of work of the Lorentz force. Okay, so first looking at these, the injection. This is for the largest PM, intermediate PM, smallest PM. They look pretty much alike, except that if you pay close attention, you'll see that there is a change in scale by a factor of 2 each time you decrease the Prandtl number. This maximum injection, this is the spectrum of this thing. This maximum injection actually corresponds to the K of the most unstable channel mode. And the critical K, that is all channel modes get shut off by magnetic tension, is right here. Same thing here, same thing here. So we kind of find something which is reassuring, that the injection is really related to the linear instability in some sense. If I had concluded otherwise, you probably would have thought that this talk is bullshit. But so that's for the injection. The dissipation. Okay, if you look at this one, you notice that it's barely resolved, actually. Prandtl number of 1 is barely resolved at Reynolds number of 20,000. But it's still okay if you look in the shape of the spectrum. But the interesting thing is that there is some modest scale separation between the kinetic and the magnetic energy. And there is, if you remember the previous thing. I'm going to show that in the next one. There is some reasonable scale separation between injection and dissipation. And you do see some kind of hint of an inertial spectrum. Well, just for the eye, this is the Kolmogorov spectrum. There is no reason to believe that the inertial spectrum should be really Kolmogorov. And the dip here is real, actually. It's related to the transfer term I haven't discussed, and I don't really understand them. So that's why I don't discuss them, but it's related to that. The important conclusion here is that there is, in this situation, we are in small Prandtl number regime. It looks like there is no inverse cascade. It's not quite sure yet, but it looks like there is no inverse cascade. And that's very different from what's going on at large Prandtl number, especially in the dynamo problem that Sébastien has talked about. Okay, so what does that mean for the very, very small Prandtl regime? Whatever is going on here, it's an energy spectrum for velocity, in principle, what's going on. So you have here the magnetic energy dissipation scale and the viscous dissipation scale here. The only thing we can say for sure, I think, in this case, is that in between here, there will be a Kolmogorov spectrum. It's just pure hydro. The field has, magnetic field has gone down. It's pure hydro. Information is transferring down. So if you change the Reynolds number that is changing this thing here, it should not affect the transport. It means that in the very small Prandtl regime, you do expect that the transport is not dependent on the Prandtl number, but just on the magnetic Reynolds number. So at some point you should you should stop having the Prandtl number dependence. We don't have it yet, but at some point you expect that you'll have it just because of this. So can we guess where we are from this saturation, this absence of dependence of the Prandtl number? If I look back at the three runs I've just shown, I kind of guess that you need to achieve at least a Prandtl number of something with the order 1/10. Well, it's the other way around, smaller than that. and the scale separation between injection and the resistive scale, which is at least a factor of 5 to 10. And then you'll get an alpha, which is probably independent of both the Reynolds number and the magnetic Reynolds number. Independent of the Reynolds number because of this argument, independent of the magnetic Reynolds number because there is probably no inverse cascade. It's an optimist guess. That still takes us into millions of CPU hours because you need to achieve a double scale separation here. That's the main trouble in this business. You need to achieve a separation of scale between the injection scale, the resistive scale, and the viscous scale. Just having one scale separation is already horrendous numerically. Having two is really, really terrible to do. But it might be doable.
That type of argument, when you say there should be no Prandtl number dependence at all? Because if you go to extremely high Reynolds number, then there should
if I go to extremely high Reynolds number, I'm in this case. And whatever's going on here should not care if I cut the cascade here or here.
take both K eta and K nu to very, very high K.
If what?
Take both K eta and K nu to very large values. If the dissipation is really small, then I would argue that everything at smaller scales than that wouldn't care about that dissipation scale, in which case it doesn't care about
Well, this is true if there is no inverse cascade. If there is an inverse cascade, you do care about the fact that you are accumulating energy at this scale. If there is whether or not there is an inverse cascade in the magnetic field, you're certain that the Reynolds number will not be important at some point because information transfers this way in this range of scales. Whether you're going to be dependent on the magnetic Reynolds number or not is a question of having or not an inverse cascade. Basically, that's what I'm saying. Okay, so to go back to this diagram, what can we say? There is something I didn't mention, which is, it's all right, and it's almost my last transparency. It's the next to last. I didn't mention that the transport for this vertical net flux problem is not dominated by axisymmetric modes, by the channel modes, but it's dominated by non-axisymmetric modes. So at least you have to include all MRI modes. If this diagram has any relevance to the problem, you at least need to include the non-axisymmetric modes in it. It looks like it's the source is really the linear instability. That's the diagram I showed about the injection. Secondary instabilities might be what's destroying the MRI modes. They might be the parasitic modes and are probably other types of secondary instabilities that we don't know about yet. But the thing here is that it will be impossible, in my view, to conclude about the transport level, the transport saturation, without characterizing that part of the three legs problem. It has been ignored until now because we basically know nothing about it. But I kind of guess that it's impossible to conclude about transport saturation without knowing something about that. Okay, so conclusions. I tried to make them brief. The existence of a Prandtl and field strength depends on the transport doesn't seem to be related to linear physics. The details of it might, especially if you don't reach high enough Elsasser numbers, but the existence of it doesn't. The saturation of the transport is not simply related to some interplay between channel and parasitic modes for linear instability and secondary instabilities. It looks like there is, in the small Prandtl number regime, that there is no inverse cascade in the next flux situation, in which case we might hope that at some point the transport will become independent of the dissipation, basically. And on this project, other things are in progress. The effect of everyone is worrying about that, and it's important. Compressibility and stratification. That's ongoing things with Sébastien. And we're also trying to constrain the dynamics from nonlinear solutions in 2D and 3D. And that's with all the other people described here. Most of them are in the audience, actually. And but it's still extremely preliminary. Okay, and that's it. Bing.
I was just wondering about whether or not there's an inverse cascade might depend on the beta, because if Sebastian's hypothesis is true, that in the net flux, zero net flux case there is, and you're saying there isn't for some beta, I mean, is there some marginal beta for which?
I think it's the Prandtl number which makes the difference. If you, for example, if you look at the dynamo problem, there is a clear difference between large Prandtl and small Prandtl.
Yes, no, I know, yeah.
Sébastien sees things in the net flux only in the large Prandtl, well, larger than 1. We don't know what's going on in the small Prandtl. Right. So the important thing to check now is to try to catch something in the zero net flux at Prandtl smaller than 1, and then we'll know.
So I misunderstood. You're claiming that there's no inverse cascade for any Prandtl number in
no, not for any Prandtl number.
So I'm trying to understand it completely.
For Prandtl numbers smaller than unity, I would guess that there is no inverse cascade.
What when it's bigger than 1?
Sorry?
What is the situation when the Prandtl number is bigger than 1?
Why is there a difference? I don't know. I noticed there is a difference. I'm not sure I understand the question.
Well, I'm just trying to see what the connection between the net flux.
The net flux and the zero net flux. Okay.
In terms of whether there's an inverse cascade or not.
It's obvious that when you decrease beta, and at some point you're going to reach a zero net flux problem. In Prandtl larger than 1, it's about beta order 10 to the 5, 10 to the 6. It's when you kind of connect the mean flux to the zero net flux. On the other side, we don't know. But because there is a connection, if there is no inverse cascade, kind of strange. Anything might happen, but it would be kind of strange that you wouldn't have an inverse cascade with a net flux and would have one with a net flux. Now, But that might happen. Now, if you look at the transfer term, an injection term, that's also related to a question that Geoffroy has asked earlier. That's one of Geoffroy's simulations for the zero net flux. Reynolds 25,000, Prandtl equals 2. And there is a significant difference with respect to what Sébastien showed, and I don't really understand it. It's in the injection. There is a dissymmetry in the injection. You inject things all the way to the dissipation scale. And that's in my view, related to the fact that you get a bump into the magnetic energy spectrum. In his simulation, it didn't show, but also it didn't show the transport. It showed the transport just for one component of the field. So that might be the difference, I'm not sure. So this thing is pretty extended all the way to the dissipation scale. If you look here, it's not true. You shut off, for almost all Prandtl's number, you shut off significantly before the dissipation scale. So that's why I believe there is no inverse cascade. And you can also look a little more carefully about the transfer terms that I have not shown there and kind of suggest that this is true, but it's still subject to discussion, of course.
I think we've run a little bit over in time, so maybe we should continue the discussion over coffee, and let's come back at 11:35.
Okay, sorry for that.
No, it's my fault.